Damn it, you people.
It's okay. I walked through it entirely with what should you expect to see in an infrared spectrum because 6 months ago I didn't know. How are you? I'm really bad at looking at schedules, so I just saw that you're. I was like, oh, pretty good. Pretty good. This is the session I'm yeah. Also very much looking forward to it. I was saying, I think that's really recently. Hopefully. Well, we have new things. I'm not talking about one yet. Yeah, that's right.
It's like a red sunlight.
Oh, is that how did it turn red when you're passing time?
No, there's a little guy with the flag.
Do this now colloquially anyway.
Can I say one thing real quick? I realize I'm not going to change the talk. I've already done what I need to
Today at 1:53 p.m.
do. Oops.
As opposed to my today at 1:56 p.m.
I just want to make sure some of the things build correctly. Okay. Pretend you don't see this. Okay.
So. Yeah, it's doing weird things. Yeah, what is one yesterday. Yeah, we're actually now.
We're outside.
It's like a long meeting and like doing some little funky things. Like the precision spectrometry calibration to see like what's actually wrong. Like, ooh, that's a really good point. So we're gonna have to, yeah. Calibrations. It may have some of the things, I think that's what some of them are different orders. So yeah. We'll see. I think it's gonna probably have a minute. But it's not, I'm like, if I get another probably.
Yes.
I don't know what's doing, but my mind is okay. Yeah, it's like, it's just like,
But you're
Yeah, it's the.
Yeah.
Part of the soft is camping. But soft is really good stuff. So I'm working right now.
I know I was,
No, I was really beautiful. That's almost too easy. There's so many people at MIT who are working.
yeah, it was.
Now we're working on it. There's maybe some kind of data, but I need to also be much more. Yeah, that's like, there's enough there that you learn. Go through the painful So the second one is usually before I usually search direct.
No, it was great. Nothing else.
There's one to work with. Yeah. Is it yeah. There's a very fun competition. It has a.
Yes.
No, I'm not just saying yeah, we're gonna start to build up a statistically so we can get enough samples. We can also start seeing things at different velocities. Yeah. So, but you can't do that. I don't know. But I would expect to see things at like 29. Yeah. I feel like. Yeah, exactly.
Very big.
I was gonna say, I hope this was No, somewhere.
Sorry.
Great, so I'll give you, the outposts.
Alright, do you know how to work everything? I'm gonna monitor the Slack. But this is the timer. Well, you can do whatever you want. You can do the alarm. You're right. 20 minutes per invited. 12 minutes per.
Where's my chair? Huh? Where's my chair? You didn't stop already. The extra 20 minutes of today.
Yeah.
I would.
Yeah, I know. I told him, no, yeah. It's not a war. I don't want to be something else. Yeah. Ah, I really. Huh? Yeah, that was so great. What's been where? Oh, that's mine. That's mine.
Are you eating it right now?
No, I ate it. No.
What?
I'm not sure that's true.
Millions.
I've never heard that.
No
Yeah,
food or drink.
Well, officially no, but unofficially. Why are you telling me after that sign?
Yeah.
I mean, people definitely ate it.
Initially, and then my.
Okay.
Okay.
What makes people?
Let's do okay. Let's get this on there. Okay. Great.
There'll be enough seats for everybody.
Yeah.
But you can get just like maybe remind everybody to move like to move
Good idea.
because during the last session we took.
All right, we're just about to get started. Please have a seat. If you need more seats, you can come around this way. If people can move in towards the center, that can help too.
Okay, welcome everyone to our afternoon session on tidal disruption events, AGN, and nuclear transients. Our first speaker is Yuhan Yao, who's going to tell us about high energy X-ray observations of tidal disruption events.
So hello everyone, my name is Yuhan Yao. I'm a Miller postdoc fellow at UC Berkeley, and it's my great pleasure to come here and talk to you about high energy X-ray observations of TDEs. So as you have heard this morning, tidal disruption events happen when a star comes too close to a massive black hole in the galaxy. So this happens if the star is within the tidal radius where the star's self-gravity equals to the tidal force. Typically, for a 10 to the 6th solar mass black hole, the tidal radius is half an AU, and in order to get electromagnetic radiation, we need the tidal radius to be outside of the black hole's event horizon. Otherwise, there is no light coming out. And this sets the maximum black hole mass of an observable TDE to be around 10 to the 8 solar masses. The early theory also predicts that the initial mass fallback rate will initially rise for a month to a peak rate that's highly super-Eddington around lower mass black holes. The returned stellar debris will quickly circularize to form a compact accretion flow. And for a super-Eddington thick disk, the viscous timescale is short, so the mass accretion rate is expected to closely follow the mass fallback rate that has this characteristic T to the minus 5/3 decline. The very first TDE discoveries were made with the ROSAT X-ray satellite more than 3 decades ago. The discoveries of those soft X-ray flares in the center of quiescent galaxies are really telling us that we are seeing mass accretion onto massive black holes. Over the past few decades, we've seen a surge of TDE discoveries. This figure is already outdated. Right now, we know more than 200 TDEs. And we've come to appreciate that TDEs are really multi-wavelength phenomena. The UV and optical wavelengths track the reprocessed emission in some optically thick outflow and the radiation produced by the debris stream collision shocks. The infrared tracks TDEs in obscured regions as well as dust produced by TDEs. The radio probe the interaction between some outflow or jets launched from the TDE and the ambient circumnuclear medium in the galaxy. The X-ray is different from all of the above. It probes the hottest regions in the system, regions that's closest to the black hole's event horizon. So to understand black hole accretion and jet physics, we need an X-ray to tell us what's the timescale of accretion disk formation, what's the timescale of state transitions between some super-Eddington and sub-Eddington regimes. What does massive black hole accretion look like? And how often do we see relativistic jets being launched? How are the particles accelerated and energy dissipated within the TDE jets? Another motivation to look at TDEs in the X-ray is that if you want to use TDEs to probe the most interesting population of intermediate mass black holes, they may only shine bright in the X-ray band. I say this because among the 200 TDEs that we know of, 2 of them are hosted by intermediate mass black holes with a black hole mass less than 10 to the 5 solar masses, and they were both identified in the X-rays, which we will see later. This may not be a coincidence because if we assume some Eddington-limited radiation, then the inner disk temperature is higher when the black hole mass is lower, and the disk radiation will be shifted more into the soft X-rays. Also, relativistic GR effects is weaker around lower mass black holes, so we might expect less stream-stream collision that produce outflows to reprocess the high-energy X-rays. So we can only do X-ray observations from space, and here I want to highlight a few recent TDE observations made by X-ray satellites shown here. NICER and SWIFT have been very important to get early-time high-cadence observations, as well as to track the long-term monitoring of the TDEs. XM Newton, NuSTAR, and Chandra are able to conduct long-stare observations, which enable very detailed spectra, timing, and astrometric analysis. SRG and Einstein probe all have very powerful discovery capabilities, so I want to start from them. The 2 discovery engines are the ULTRASAT telescope on board of SRG and the Wide Field X-ray telescope on board of EP, which is also recently named as the Tianguan satellite. So both of them operate in the soft X-ray regime. ULTRASAT is currently not in operation, but in the early 2020s, it has conducted a bit more than 4 all-sky surveys with a 6-month cadence. It is very sensitive and can typically localize sources to a few arcseconds. EP has much shallower sensitivity and poorer angular resolution, but thanks to its lobster eye X-ray optics, it has this very large field of view that's almost 1/10 of all sky. So depending on your different science goals, they have different advantages. ULTRASAT is certainly very good at finding a large sample of TDEs in the X-ray. So here is a sample study presented by the German ULTRASAT consortium presenting 13 TDEs selected from the second ULTRASAT all-sky survey that have non-detections in the first. So you can see that all of those events, because they have very good contemporaneous optical coverage by the ZTF and ATLAS surveys, we can constrain what's the peak luminosity of their simultaneous optical flares. And it turns out that this population is intrinsically faint in the optical. Similarly, because this is a systematically selected sample with a well-understood survey efficiency, they can constrain what's the luminosity function and volumetric rate of X-ray selected TDEs. And it turns out that this population is comparable and maybe a factor of a few rarer than optically selected events. Down there are some single object papers published by the German ULTRASAT consortium. This is only the tip of the iceberg of the ULTRASAT TDE sample, and more sample papers are there in preparation. EP was only launched last year, so there haven't been many TDE publications. But the very first TDE discovery, EP 240222A, is very interesting. So here you can see the X-ray light curve on the top. The EP data is shown in green. The orange one shows data from the LEA satellite, which is an EP pathfinder. And this source also happens to have a rising part of the light curve in the ULTRASAT survey. So you can see that it has a very long rise time. Down there are force photometry shown in black from the ZTF. So the source is intrinsically faint. It only has a 21 magnitude optical flare. What's really interesting is the location of this X-ray transient. So here you can see the X-ray transient is on top of a very faint optical smudge in the legacy survey image, which is consistent with a disrupted satellite galaxy that's 35 kiloparsec away from the center of a bigger galaxy. So this small galaxy, you can do some ICD fitting. It has a total stellar mass of 10 to the 7 solar masses. So you can constrain the black hole mass of the TDE using two methods. One is to scale from the galaxy mass using some scaling relation, or you can fit the X-ray spectrum using a thermal model. And both methods give a black hole mass that's a few times 10 to the 4 solar masses. This is actually the second intermediate mass black hole TDE that we know of. The very first one was found by archival searches of soft X-ray flares in the in XM Newton and Chandra archives. So here, this event, 3XMJ2150, you can see its light curve over many years has this characteristic power law decline, and it has soft X-ray spectrum. The location of the X-ray source is here marked by this green circle, which is spatially coincident with a marginally resolved optical source. And this is also some 12.5 kiloparsec away from the center of a bigger galaxy. So I think the discovery of those two objects really demonstrate that X-rays holds the promise to find more of those TDEs powered by lower mass black holes and to probe intermediate mass black hole demographics. In addition to finding TDEs directly in the X-ray band, we have also learned a lot by following up optically discovered TDEs using X-ray facilities. So here I want to highlight a study by Muriel Gullo at JHU, where he systematically analyzed Swift and XM Newton data for 17 optically selected TDEs with X-ray detections. Among them, 13 events have good X-ray temporal coverage, so he can classify the light curve shapes into different categories. And what he found is that the TDE X-ray light curve is really diverse. In about half of the 13 events, he observed this delayed X-ray brightening that peaks around 200 days after the peak of the UV and optical flare, as it's shown in AT2019 AZH. So the idea is that maybe at early time, you have more optically thick outflow that represents the high energy emission, but later on, the optical depth through the outflow drops, so you'll see more into the inner disk accretion. In another 3 events, he found very persistently faint X-ray emission, such as shown in 18ZR. In another 3, he found monotonically declined X-ray light curve over many years, such as in Assassin 14 Li. And in one event, he found this very large amplitude flare on the timescale of a few days. So if you look at their early time ICD, they look very different from each other. So here are Assassin 14 Li, 18ZR, 19AZH, which we have shown before, as well as adding here 20 ZSO, which does not have any early time X-ray emission. This type of diversity is exactly what is expected from the unification model proposed by Jin Dai, where depending on your viewing angle relative to the disk axis, you see different parts of the system. So if you have a more face-on view, you see more into the direct accretion disk emission in the soft X-ray, and going to an edge-on view, you see more reprocessed emission that's in the UV and optical. We're not saying that this is a correct model for every single event, but at least some of the properties predicted by the model is present in the data. So this is a sample study. And we have also seen some surprises from very detailed X-ray monitoring campaign on each individual event. So one surprise is seen in nicer observation of the TDE-AT 2022 LRI. Here, the nicer data is shown in blue and SWIFT data shown in red. You can see this very large amplitude dips on top of a longer power law decline. If you zoom in, you can see that the variability timescale is really on the timescale of less than an hour, and it's non-periodic. So the idea is that this might be caused by some magnetic instability in the superidential accretion disk or the wobbling of the inner accretion disk along the spin axis. Another surprise, which was also covered by Brian, is the discovery of quasi-periodic eruptions or QPEs later on in some TDEs. So this is X-ray observations of one flare roughly every 48 hours, a few years after the TDE-AT 2019 QIZ. So this supports some of the models that link TDEs and QPEs together. Specifically, you can have an initial extreme mass ratio in spiral that's consisting of a main sequence star and a supermassive black hole. There's no way you can see it unless a few years later there is another star come as a TDE that provides a new accretion disk, so that every time the previous star interact with the newly formed disk, you can see a flare in the X-ray. We have also made some progress in understanding the TDE X-ray spectrum. So previously, we know that fast and slow outflows are ubiquitously predicted in black hole super-Eddington simulations. And now I think whenever we have an X-ray bright TDE and we observe it with an X-ray detector with enough effective area, then fast outflows can be ubiquitously identified. So here I'm showing one example, again in AT 2022 LRI, where its soft X-ray spectrum cannot be purely modeled with some disk. There is this strong 1 keV feature, but this can be well modeled with some outflow with the outflow velocity that's between 0.1 and 0.3, the speed of the light. Detecting slow outflow is more challenging because that requires grating instruments that provides a higher spectral resolution. One example is shown for the RGS observation of Assassin 14 Li, where you can see low velocity, narrow absorption lines that's all blue shifted by a few hundred kilometers per second. Although the vast majority of non-jetted TDEs are soft, we do observe hard X-rays in some events. So among the 17 TDEs that Muriel analyzed, he identified hard X-rays in 3 of them. That's AT 2018 FYK, 2020 OCN, and 21 EHB. All of them developed hard X-rays a few hundred days after the optical discovery. So those events are hosted by black holes that's about 10 to the 7 solar masses, which is on the high end of the TDE black hole mass distribution. So the idea is that because they have a higher black hole mass, they can achieve sub-Eddington accretion earlier. And if you have sub-Eddington accretion, then it's easier to form a magnetically dominated corona above the accretion disk, where you can have inverse Compton scattering of the thermal disk photons to produce the high energy hard X-ray band part. More recently, we identified hard X-ray in the TDE-AT 2022 KMQ at even earlier time. And this object is hosted by a black hole with a mass as 10 to the 8 solar massage, which is even higher. For AT 2021 EHB, we managed to get nicer and new star spectrum that give us a broadband X-ray spectrum out to 30 keV. And here we can identify spectral features that's characteristic of disk reflection. this type of modeling allowed us to constrain that the ionization state of this TDE disk is higher than what is typically seen in AGN disk. Another place where you expect hard X-rays in TDEs is those events that launch relativistic jets. So among the 200 TDEs that we know, 4 of them are associated with on-axis relativistic jet, which is a small fraction of the population. 3 of them were discovered by Swift Burst Alert Telescope, and AT2022 CMC is more recently identified by ZTF. You can see that they are very luminous, extragalactic X-ray transient, have short timescale variability on top of some power law decline. Until between 100 to 300 days, the X-ray suddenly shuts off, which may signify the jet shut off, because previously you have a super-identity accreting thick disk, which can thread the magnetic flux to hold powerful jets. But once your mass accretion rate drops, it transitions to a thin disk, which cannot hold much magnetic flux anymore, so the jet shuts off. We also want to understand the jet physics better, so a broadband X-ray spectrum is very important. For AT2022 CMC, we managed to get nicer NuSTAR and Swift spectra during the first few days of its evolution. And we see that the broadband X-ray spectrum is a broken power law, and it remains a broken power law for a few days. So this is consistent with synchrotron emission from the jet, where the particles are accelerated by magnetic reconnection instead of internal shocks. Okay. So far, I've been talking about TDEs powered by a black hole in the center of some galaxies, but there's no reason to not expect TDEs powered by a black hole that's not in the galaxy center. So one recent example is AT2024 TVD. The optical location of the transient is shown by this red crosshair, which is actually 1 arcsecond away from the center of the galaxy, and is well within the galactic bulge. The off-center location was also confirmed by HST observation. And the reason that we believe this must be a TDE instead of a supernova is because Swift XRT shows very bright, highly variable, soft X-ray emission that's a few times 10 to the 33 ergs per second, which is just too luminous for a supernova. And what's also really important is that Chandra observation demonstrated that the X-ray transient is associated with the optical transient. The location is shown in the cross, and it's also offset from the center of the host galaxy, shown in this red plus. So I think it's really fascinating to think about how you can create a wandering black hole. One way is that during a minor galaxy merger, you can have a very long dynamical friction timescale such that the merger of the black hole is significantly delayed from the merger of the galaxy. Another way is that you can have some dynamical processes in the center of the galaxy that eject one of the black holes to off-center location, creating some recoiling black holes. So it will be really nice to find a growing sample of nuclear TDEs with future sky surveys. And I think telescopes with good astrometric capability will be crucial to identify their off-nuclear natures. So yeah, I think characterizing TDEs in the X-ray is not only important for us to understand the high-energy astrophysical processes, but also it provides a window where we can use TDEs to understand how the black holes evolve as a function of cosmic time via galaxy mergers. So with that, I'm leaving my summaries here, and I'm happy to take any questions.
Questions?
For that beautiful last case that you showed, is there a spectrum for the?
Yes, so there is HST UV and optical spectrum. In the optical, it has broad hydrogen line. In the UV, it looks exactly the same as the SASN-14 Li.
I just asked about this recoil model. So if you have a black hole that's recoiling out of the nucleus at some significant velocity, how likely is it to be able to disrupt a star?
Yeah, you need a star cluster to remain bound to the black hole. Otherwise, the rate is too low. And it needs to, if the velocity is about 200 kilometers per second, the eject, then a fraction of the nuclear star cluster will not remain bound. So I think some simulation to calculate what fraction of the nuclear star cluster can still be there would be important in the future.
I have one comment maybe. We recently the IU approved officially to use TDE as instead of AT as the part of your name. So instead of saying TDE AT so and so, you can just say TDE so and so if you like. It's already updated on TNS.
Okay, thanks.
So for the source with X-ray reflection, is there any way to constrain the spin, or do you have a spin constraint?
So for that source, we can't because it's not sensitive to the spin. Because it has such a high ionization state, all the features are so broadened, and different spin give you very similar results. Mm-hmm.
Great, let's thank Yuhan again.
Should I use these?
Yeah.
Okay.
Okay, next, I practiced this. We're going to hear from Christos Panagiotou.
Wow.
Okay.
That's perfect.
On identifying mid-infrared nuclear transients and their connections to neutrinos.
Okay, thanks, Suvi. Hi everyone, I'm Christos. And now today I would like to tell you a bit more about TDs specifically that we find in WISE, using WISE archive. Kishel already mentioned some of it, but I want to give you a bit of a story, how we started, why we thought it might be interesting, and what are the next steps, what we're thinking to do next. So we already heard from Yuhan a very nice talk about TDs in the X-rays. And here is also a plot that Suvi put together a few years ago that you see all the known TDs at the time. And one thing you can notice is that there is no TDs in the infrared, like at least in the plot, there is no infrared bar. So the obvious question to ask is why would someone go to the mid-infrared? And while Kishel mentioned that you can use that as a bolometer to get the accretion rate, the energy that's radiated, I'm coming from AGN, so my initial thought why this might be interesting is because in AGN we do know all the accretion features are typically in optical and X-rays, but if you have absorption, these are all get very well diminished due to galactic emission, while in mid-infrared you still get the AGN features, you don't lose them. So that's that was my initial motivation why this might be interesting. Well, that's a bit theoretical. Do we know, do we have any indication why we might want to do that? And it turns out there were some tensions back then that kind of hinted in a hidden population of TDs. One is that the theoretical rate for TDs was found to be a bit lower than the one that is estimated from surveys. Now that's a bit, as a result, there are a lot of assumptions estimating these two rates, so it's not that important, but the most important that a lot of people know about is that TDs found in the optical and also X-rays are typically found in post-harvest galaxies, in Green Valley galaxies. And to show that more in a plot, you see here the UR color versus the stellar mass of the galaxy, and you see that both in the optical on the left and on the X-rays on the right, TDs seem to be occupying mostly galaxies in the Green Valley and not in the blue part, in the star-forming part where we would expect to see a lot of TDs or of comparable numbers. And a few years ago, there was this paper by Roth and collaborators that came out and suggested that while this might be a real effect, and if it is, there's a lot of work that has been done in that to explain what kind of galactic, stellar dynamics in specific galaxies could explain that, there is also a potential that this might just be a selection effect. Because in star-forming galaxies, you might have a larger amount of dust, and then you're not going to see all of these TDs in soft X-rays and optical. And we thought, okay, let's go and test that. To do that, we used WISE. Okay, Kishel already introduced that. I don't have to spend my time. Just wanna, to be fair, we're not the only ones that we've been doing that. There's another group, the MIRON group, which stands for mid-infrared outburst in nuclei of galaxies, I think. And they've been working more or less in parallel with us. There are a few differences. They use integrated photometry, and they only study STSS galaxies, while we go, more broadly, and we do difference imaging. And these allow us to be complementary, but more or less we find very interesting results that kind of agree with each other. And we do the difference imaging the way that Kishler already presented, so I don't have to explain that. And here's the first source we found. And that's a nuclear transient found in a nearby galaxy. And the first thing that we have to answer when Kishler came and showed that to me was, okay, what is that? So the obvious way to go, and answer this question is to look what people have found in optical surveys and try to understand which one of these optical transits could explain this one. Obvious possibilities, AGN, supernova, TD. And long story short, as Kishler said, we can exclude supernova because the energetic outcome of this burst is crazy huge. We can exclude AGN because there is no X-rays and from the optical spectrum through the BPT diagram. So the only viable option that we are left with is TDs. So we concluded that excluding everything else, this has to be a TD. The interesting thing again, that's the closest TD ever found. And we do have X-ray surveys and optical surveys looking for TDs for for a decade, let's say, or more than a decade. So it was very surprising to realize that the closest TD we know is the one that we randomly found by doing this exercise on archival data. At the same time, you can see there is an optical emission, right? So it does align well with the argument that may be a hidden population of TDs that different surveys have missed, and that's why we have this kind of over representation in a rare class of galaxies. And indeed, this is the case. Like for this TD that I just showed you, the host galaxy lies in the star-forming region of this plot, and you can actually even see it in the image of the galaxy. And the cutout is like a blue star-forming galaxy. So it all came together, it kind of made a nice story. This was already a bit more than a year ago. So then we're like, okay, clearly there's a hidden population, and most likely this hidden population of CDs is not what people find in the optical and X-rays. So we came together, and actually Megan is the one who took over and created, found a volume limited sample with several TDs in the nearby universe. And Megan is going to be talking about that, so I'm not going to spoil any of her really impressive results. I just want to say, one of the main outcomes that it's important is that there are a lot of TDs that we don't find in any other survey, and they're all very nearby, and they do hint in a specific population. And then, Megan finalized this work a few months ago. It's all up, or a year ago, I don't remember. But then the question was, where do we go from there? Now we do know that these TDs exist, but also it's a very time-consuming analysis. Like the work that Megan did is a volume-limited sample, which allowed us to have small amount of nuclear transits that we could go and do optical spectroscopy and X-ray follow-up and all of that. But people who have done this exercise, they do know, that's very time-consuming and resources-consuming. So we cannot just do that blindly, because a large fraction of nuclear transits is going to be AGN and supernova, unavoidably. So I have a student who's been working on creating a new classification criteria to try to get the best TD candidates just by WISE light curves. And in this case, we don't use only WISE light curves, but we use WISE colors. So for people who might not be familiar, the WISE color is a good indication of AGN activity if it's above 0.8. And we realized that for most of our sources, it's not the case. I mean, if it was, it wouldn't be a TD. But also, it has the color evolution of our TDs. They have a very specific shape, which is the one you see here. And it's very unlike the shape of AGN, variability in WISE. So we went on and we created this criterion. The student Prajaner is finalizing the work, and actually we now do follow-up for the good candidates, and we see that the criterion work. Like we can say that we do have a new mid-different criterion to select good TD candidates. And why am I saying all of that? Because I think this is very important for the future, for Roman. I know a lot of people in the room are thinking about Roman. Roman is, it's going to have a very high, very large field of view. It's going to be conducting this so-called high latitude Time Domain Survey, which I think we're going to hear more about tomorrow. But what's important, what I want to highlight out is, Roman is sensitive in near infrared, which is between the optical surveys and WISE. So with its wide field, Roman is destined to find a lot of TDs in this survey. And because it's sensitive in near infrared, I do expect that probably Roman is going to be able to detect sources that are visible in both optical and mid-infrared, or at least get most of them, and then it's going to be a nice way to get a complete population of TDs. Try to understand what are the differences between the two populations, what more we can tell, especially if we combine Roman with missions like ULTRASAT or UVEX, which are going to be operating at the same time. How am I doing from time? Do I still have?
We have 4 minutes.
Oh, perfect. Okay, so one more thing I want to highlight is another work I've been doing with a student. So, time domain astronomy is usually, the short name for that is TDAMM. The thing is multi-messenger, and that's because transients are usually considered good sources for multi-messenger astronomy. And here is one example where TDs have been claimed to be one of these sources. So what you can see is on the left first is 3 TD candidates that seem to, coexist in the sky with neutrinos, neutrino events, and similar results were found from another group a few years after the first detections. And what is interesting to notice is that the arrival of the neutrino is at the same time as the peak of the infrared flare, of the infrared emission from the TDs, and not the peak optical emission. So, Shortfall, Bezer, and collaborators try to use this clue and try to study, is that actually there is a real correlation between TDs that are bright in infrared and neutrinos. And they, did some specific statistical analysis, and they concluded that yes, if the infrared flux and neutrino flux are correlated, which is what you see on the right, where the field points are the 3 sources that have actually the neutrino association, then there is a highly statistical hypothesis. They can prove the hypothesis with high confidence that there is a connection between TDs and neutrinos, or infrared bright TDs and neutrinos. So I realized at the time that finding neutrinos in WISE means they're definitely mid-infrared bright. So this might be the best sample to go and test if there's a connection between TDs and neutrinos. And I had another student, Megan Wang, who's an undergraduate in MIT right now, and she did exactly that. She collected all the mid-infrared accretion flares from the nearby universe that could be good TD candidates, and cross-match them with the latest IceCube catalog, the so-called IceCat1. And here you see, the sky position of all of that. And what she found is that there is no connection between the two. There is no, in the terms of coincidence in the sky, there are 3. But when you put in the temporal information, there is no really any coincidence between the two. Not only that, she showed that, here's the same plot as before, where you have again the infrared echo flux as, as a function of dust echo strength. This is what people use to claim that infrared flux and neutrino flux are correlated. What she found is our sources are actually much, much brighter infrared than all the sources that have been used before. So kind of disproving the point that, neutrinos and infrared bright TDs are connected. And am I done, I think?
Yeah.
Okay. No, that's fine. So I'm going to stop here and thank you all.
Question. Yes.
This might be a question for the next talk, but I'm going to ask it either way. Do you have a sense for, does Roman go red enough to discover the transients you found going twice? Because if they're obscured in the red, but Roman doesn't go that red, do you still try to find these type of things?
I think, well, Roman is not going to find all these we find twice.
Yeah.
But a good fraction of them, they should, because they're not found in optical, they're obscured, but they're not obscured to the level that are completely obscured in near infrared.
Yeah.
Lots of them, they have AV that would allow you to detect them in near infrared. Well, that's a good question, and we try to address this question right now by also, combining with near infrared service before Roman goes in.
Wondering at what wavelength that starts to show up.
I think you might.
Yeah.
Yes, DJ.
So you said you correlated with the IceCube. Oh, so I see that. Golden. Oh, you only use the gold sample, not the bronze.
Yes, I mean, I want to have at least 6% probability of having astrophysical origin, yeah.
But also, what about the volume? Is it volume limited sample with your IR? I'm just wondering, how do you consider Are you just doing spatial correlations? No other cuts?
And plus temporal correlations.
Yeah, I want to talk to you more.
Go ahead.
Two quick questions. One is, what is the mass in the nearby TE that you found of the black hole? And the other one is if there's any hope of getting hard X-ray emission.
So first one, mass, I think it was 7 point something, 10 to the 7 point something, the black hole mass, and comes from the M sigma relation. The other one about, you said hard X-rays?
You said you don't have any X-rays, but would New Star have it?
No, there was no X-rays in this first source, but in what Megan found, there are, some like 3 out of 8 or something with X-ray detected that happen to have X-ray, coverage at the time. About hard X-rays, I would say even less, like probably 10% or less, because these in general, they don't produce hard X-rays. Yeah.
So changing look AGN or flaring AGN also have really nice dust echoes. So are those in the original sample, but then you based on the optical spectra of the host galaxy?
Yes. I talking about the mid-different criterion that I try to.
I guess in general, when you guys, there must be a lot of pick up a lot of AGN.
Yeah. So they don't even if we're talking about changing look AGN, they don't follow this, or most of them don't. Like the Wise color evolution does not look like that.
Okay.
But at the same time, for all the good candidates, we do get optical spectra. And then, if they have line or if they're, they have lines up from the BPT, they seem to be AGN, we exclude them from that.
All right, let's thank him again. Okay, next we'll hear from Megan Masterson on a new population of mid-infrared selected tidal disruption events. Great.
Okay, all right. Hi, everyone. My name is Megan Masterson. I'm a grad student at MIT, and I'm really excited to be here today to continue our discussion of tidal disruption events, and specifically this mid-infrared population that Christos was just telling you about. So I think now you've heard 2 talks that have exclusively talked about the search for dusty TDEs, so I'm going to go very quickly through the introduction. But one thing that I want to highlight is that, yes, the majority of this infrared emission is coming from this reprocessing, this intrinsic emission in the optical and UV by the dust. And this was initially discovered in optical TDEs. We can see these echoes, but they're relatively weak. So this is one of the first TDE dust echoes that was observed in 2016. There were a flurry of papers on the archive all at the same time. And the reason why these dust echoes are so weak compared to the optical emission is that the covering factor is relatively low. So that's my little schematic on the left-hand side here. And so what we're going after in the infrared is sources that look more like this. And this is, as people have already highlighted for you, the infrared might be one of the only ways to go after detecting these sorts of sources. So with Kishley and Christos at MIT, we've been working on this sample of this volume-limited sample that Christos alluded to, using the WISE transient pipeline that Kishley has developed. And in particular, to answer a couple of the questions that have come up, we've been looking for sources within 200 megaparsecs in the nuclei of galaxies. We rule out things like supernovae through energy arguments by looking for things that are quite bright and last quite a long time in WISE. We rule out AGN through things like WISE colors, but we also do spectroscopic follow-up to rule out AGN through narrow line emission, including these changing look AGN. So the total sample ranges from 12 to 18, depending on how many of those changing look candidates you include. So this is what I would consider our gold sample. This is 12 TDEs that show essentially no evidence for any underlying AGN activity. And you can see that we primarily see these bright optical flares or bright infrared flares with no coincident optical flare to be found. So I want to highlight kind of what this sample has told us so far and what questions that it answers, following on the questions that Christos mentioned at the beginning. So the first is this preference for post-starburst galaxies. So this is a bit of a busy plot, so I'll walk you through it. On the x-axis here, we have H delta in absorption, probing your A-type stars, your star formation on relatively long timescales of hundreds of millions of years. And on the y-axis here, we have H alpha in emission. This is probing star formation on short timescales, those hot O and B type stars that don't live for very long. So your star-forming galaxies will sit in the top right. Your passive galaxies will sit in the bottom left. And then there's the spur of galaxies that have high H delta in absorption, but no H alpha in emission, indicating that they've gone through some recent burst of star formation that has since shut off. And interestingly enough, the majority of these optically selected TDEs are found in these post-starburst galaxies, something like a 40% or 20% overrepresentation, 40 times overrepresentation. They're very different numbers. So, but when we put our infrared selected sample on this plot, this is where our galaxies lie. So we have no post-starburst galaxies in this initial infrared sample. And so the claim that I want to make is that IRTDEs are coming from a representative sample of host galaxies, including these dusty star-forming galaxies. That doesn't mean that post-star forming galaxies can't give you preferentially optically selected TDEs, but we also are finding infrared ones in star-forming galaxies. The other thing that we can start to do with this sample is address things like rates and luminosity functions. This is important when you want to talk about using TDEs to probe supermassive black hole mass demographics. We're not quite there yet with the infrared selected sample, but where we are at is we can say that the infrared rate is comparable to the optical and X-ray rate. It sits right in between the two. Our luminosity function is kind of declining towards higher luminosities, but we've yet to see the kind of turnover that you expect to see around 10 to the 8 solar masses when your tidal disruption radius goes within the event horizon. But I want to highlight that Prajna Nair, an MIT senior, is working on this in addition to those WISE color cuts. She's working on a flux limited sample where we're probing this exact turnover in the event horizon due to the event horizon suppression. So keep your eye out for more work there. So now I want to move on to talk about a little bit of the kind of follow-up work that we've been doing with this sample. One thing that we've been excited to do is work in a multi-wavelength regime. So this is work that's being led by Will Gole, Harvard PhD student. This is one of the WISE TDEs followed up in the radio at late times. And you can see there's this really delayed radio flare. Yvette will tell us more about delayed radio flares in the next talk. One thing that I want to highlight is that we're actually seeing resolved radio emission in the top left panel here with VLBA, which I think is an exciting new prospect for probing kind of late time outflows and things in the radio. With the rest of my talk, I want to highlight some recent results that we've had with JWST, and I thought I would walk you through very briefly what you should expect to see before I actually show you what the spectra look like. So in particular, the majority of this infrared emission is coming from this reprocessed emission. And it doesn't look just exactly like a black body because dust, there are things with interesting opacities in the dust. So in particular, there are silicates in dust that produce these 10 and 18 micron features. And I want to highlight that these can be seen in both emission or absorption, depending on your sight line to the dust and how optically thick or thin you are. And so this is an exciting way to probe the true obscuration level in these events. The mid-infrared is also, it has a wealth of atomic lines that we can use to probe the underlying ionization state. And then it also has two features that I won't discuss much today, but there are molecular gas transitions from H2 that you can probe, as well as these polycyclic aromatic hydrocarbons, which will also allow you to probe star formation and the underlying ionization state. So in total, the mid-infrared band is really sensitive to these obscuration levels, which are difficult to probe with just the lack of optical emission in all of our sources, as well as the underlying ionizing spectrum, which can also be difficult to probe without seeing the X-rays in particular. And also the IR is sensitive to the bolometric luminosity, and TDEs are expected to peak in the EUV, which is a band we don't have access to. But the dust is going to absorb all of that radiation. And so because it's sensitive to EUV to optical wavelengths, we can get a better sense of the total amount of luminosity and the energetics of these systems. So with WISE alone, we don't get this information. This is more what things look like. We get 2 data points from which we can extract temperature and a luminosity. But we have to make a number of assumptions about the underlying dust that goes into it. So we've been really excited. We had a cycle 2 JWST proposal that was approved, and I'm excited to share with you the data. This is what our JWST MIRI MRS data look like And you can see that it looks a lot like that kind of cartoon schematic that I showed you initially. And so I'm going to walk through a couple of pieces of phenomenology here and tell you what we've learned from this initial look at TDEs with JWST. So in particular, we see a number of lines from these highly ionized atomic species. In particular, in the middle of this circle here is a neon 5 line that has an ionization potential of around 100 EV, so it requires basically requires black hole accretion to excite gas. And in particular, we can use this wealth of information in the mid-infrared spectra, this wealth of lines, to start looking at the underlying ionizing spectrum. So what I'm showing you here is two different ratios, various neon lines that are in the mid-infrared spectra. On the y-axis here is neon 5 versus neon 2, and on the x-axis here is neon 3 divided by neon 2. Neon 2 is a strong star formation line, so our star-forming systems sit in the bottom left. And then you increase, as you move up to the top right, you increase the amount of black hole accretion that's ongoing. So our AGNs sit up there. And our WISE TDEs sit up here with the AGN, which I think is particularly exciting. We're seeing essentially the radiation from this black hole accretion exciting and ionizing the gas around these supermassive black holes. I should mention that we're seeing these TDEs about 5 to 10 years after disruption. So we're really probing kind of parsec scale dust in this case and gas. The other thing that we can do, because MIRI is an IFU, we can look at the kind of change of ionization state. And so this is just highlighting that if you extract an annular region away from the nucleus, we're not seeing that same level of TDE accretion. We can actually see that there's a change to the ionization source in the nuclei of these galaxies. The other thing that I want to highlight from these JWST spectra is that we're seeing silicates primarily in emission. And this was a little bit confusing or surprising when I first reduced the data. I was quite puzzled by this. And that's primarily because of this comparison on the left here, which is showing you, again, our JWST WISE data or WISE TDE data is shown in blue. The green and purple lines are recent MIRI MRS observations of AGN. And then there's a Spitzer mean quasar spectrum in black and a typical ultraluminous infrared galaxy shown in gray here. And you can see that we're seeing really dominant silicate emission in these JWST TDEs compared to typical AGN. And this is telling us essentially that we're seeing optically thin gas and dust from parsec scales around the supermassive black hole, unlike the typical clumpy, optically thick, dusty tori that you see in AGN. And on the right here is just showing you a comparison of the silicate strengths in WISE TDEs compared to these AGN, highlighting that we really are seeing kind of an extreme. So we've gone about trying to model this with a time-dependent dust model, where essentially what we're doing is assuming the TDE went off between 5 and 10 years ago, depending on the transient, and asking what is the expected dust temperature and then the resulting spectrum that we should see along an iso delay surface, which is essentially just a surface that describes basically all of the light from the surface will arrive to us at the same time if we have it reverberating off from this initial flare. And you can see that we do a really good job at reproducing the long wavelength spectrum, but we're missing the short wavelength emission. And one way that we can go about doing this and get around this is by basically making the TDE long-lived. And so I think that this short wavelength excess that we're seeing is evidence for a long-lived plateau in these accretion systems, where essentially we're still heating dust that's relatively close to the supermassive black hole. And this has been seen in UV observations in particular. This is Assassin 14Li, which is showing a decade-long UV plateau after that initial flare. So I'm excited about using JWST to probe these TDEs in much more detail and kind of map the circumnuclear environments of these supermassive black holes. So I just want to highlight that this is only possible because we have both survey missions to discover these TDEs, but also these dedicated follow-up missions to go after some of the detailed dust physics. And I think the future is infrared bright. With that, I will leave up my takeaways and take some questions. Thank you.
Questions here.
Very nice work, Megan. So the fact that you're
seeing optically thin dust.
Yeah.
Is that not in contradiction with the fact that these emit no optical light at all?
Yes, so I should have said optically thin in the mid-infrared. So there's a 2 to 3 orders of magnitude difference in the optical depth between the two. So I think one of the things I'd like to do next, once we get a better handle on the optical depth from the infrared and the optical, is combine these two to kind of actually test what the is like.
Yeah. Okay. So sort of in the same vein, my thinking was maybe that's different dust that's producing the echo than is providing the obscuration. Could this closer dust that's maybe producing this other component potentially be closer dust that's, you know, obscuring the optical?
That is possible. Yeah.
I'm not really a TDE person, so maybe this is a dumb question, but these plateaus, these late time plateaus, that's completely new and different, or that's sort of in keeping with what you've seen from other observations?
That's in keeping with other observations. Yes, it's like this viscous spreading of the accretion disk with time.
All of them, more or less, to do that?
Yeah, it's something like 2/3 of them are showing these late time plateaus now.
I haven't heard any reference to radio observations for these sources or any of the previous ones, because you checked and there aren't any available.
No, there are. So yeah, Will Golay at Harvard is working on this. So there's one that has this resolved jet-like structure. It's sub-relativistic, so it's not really a jet, but and it shows this delayed radio flare, just like the optically selected TDEs. And he's also working on the sample, so we're getting VLA time to close up.
A lot of VLA data as well as still being processed.
Yeah. And VLAS. So
yeah. There's one at the back there.
For the time-dependent model, you need to assume like a line of sight and also the inclination and the geometry. Is it coming from optical observations, or is it like a free parameter in the?
It's a very simple dust model. It's a spherical shell, so we're not assuming anything about the inclination. And yeah.
All right, why don't we continue the conversation? DJ, do you want to do a quick one?
Quick question is, how does this compare to the IR spectra of optically selected TDEs?
That is a great question. I'm pretty sure that work is in progress. Yeah, there are 2 Miri MRS spectra of optically selected TDEs. I have seen them at a conference only. So
sure. Yeah. All right, let's thank Megan again. All right, next we're going to hear from Yvette Sendes on new developments in late time emission in tidal disruption events.
All right. Hello, everyone. I'm Yvette Sendes, for those of you who aren't familiar. I just started this year at the University of Oregon. I am a radio astronomer, which is, I think, a lower wavelength than most of you guys normally think about. But I came to this conference to let you guys know, I know this is a space-based conference, but ignore the radio at your peril. A lot of exciting things can be happening down there. So such as late time radio emission from TDEs. So just to give you a bit of background, traditionally, when initial way when TDEs are discovered, most of the TDEs, optical astronomers or infrared astronomers, other people find them, and then we follow up with radio telescopes to look for outflows, is what's causing most of the radio emission that we're seeing. Usually within the first 1 to 2 months, when you take a look, about 20% of the time you'll see radio emission, and then traditionally people went off and did other things with their telescope time. But then there were 2 TDEs, Assassin 15OI and IPTF 16FNL, that became radio bright over 100 days after the initial TDE event happened that did not have emission at earlier times. So you could ask yourself, are we overlooking something in this general population? So to find out, we went and we looked with the VLA and Meerkat with about 25 older optically selected TDEs, 2 to 3 years old, some were a few years older, with no prior radio emission detected from these TDEs. So just to give you an idea of the timescales here and the luminosities that we're talking about. So this is without that sample added. On the x-axis, time since discovery, luminosity. This is the jetted TDE Swift J1644 plus 57. Over here, you can see Assassin 15OI. AT 2019 DSG is a very common non-relativistic outflow from a TDE that's relatively prompt, and IPTF 16 FNL. Now, if I focus on this lower region and I add in the rest of the survey of what we found, you see there's a lot more complicated things going on. And I'm going to walk you guys through this because it's a very complicated plot. But roughly 40% of all TDEs in radio have no radio emission at earlier times that turn on then at later times. So, you know, if we have a triangle, this is an upper limit. If you're looking, for example, here, we have some that are, you know, thousands of days they will turn on. Assassin 14E, I can tell you this one is still rising, actually, and we're first detected at 2,200 days after the initial TDE event happened. Some of these, you know, we have some gaps. We tried to fill it in with survey data, but we weren't really expecting this phenomenon. And then you just discover a, you know, Millijansky bright source 700 days after the initial TDE. So a lot of exciting things are going on here. This is still an ongoing process, monitoring these TDEs to understand what is happening. But the general thing here to take home is, yeah, 40% of TDEs are radio bright at later times. This is a quick histogram of just peak radio emission for all the radio TDEs that I could find in the literature. And what you can see is, yeah, it's roughly 1,000 days if you're looking for when you're brightest in radio. That appears to be a large sample of your population. Of course, it could be even higher because a lot of these are still rising. So we don't really totally understand the statistics, but it does appear that something interesting is happening at pretty late times. I'm going to devote most of the rest of my talk, though, you know, this is a very exciting population, to one particularly very exciting object of all the ones I showed you before, which is this green one here with the green stars. And this is AT 2018 HYZ. The reason AT 2018 HYZ is very exciting is, so what was the first one we published from this sample? We detected it in June 2021. It was about 1,000 days after the optically discovered TDE event happened. And when we discovered it, it was rising as fast as T to the 5th in luminosity. And we have, of course, been observing this ever since. So I was going to show you guys some of what it's been up to lately. And it's been still rising, which is kind of a spectacular thing. You saw like a lot of diversity in those light curves I showed you earlier, but none of them have been doing anything quite so meteoric, quite so exciting. You can see it's really almost, you know, at that jetted TDE brightness. Another thing to show here, I can zoom in a little bit so you can see the light curve a little bit better. What you can see is, okay, it's not going quite at T to the 5th anymore. It's only going at T to the 4. So, okay, this is still something that's still very exciting. We can keep studying it, see what's going on. We have multi-wavelength data in radio. So we have from 800 megahertz all the way up to millimeter, 240 gigahertz. We can see this rise overall at all the radio frequencies. You can see some, you know, undulations and things like that. So L-band here, for example, those who take radio data with the VLA, you know, that can sometimes be a very tricky band with RFI. That also probably has something to do with the peak frequency shifting back and forth in our SED. But anyway, the point is, this thing is getting very bright. For those who speak radio, the last observation, our peak observation was 35 millijanskys. We discovered it was 1.3 millijanskys. So it's a very bright object. But I was told to talk about other wavelengths as well. So I was going to tell you guys very quickly, you know, we're of course looking for some multi-wavelength clues. What exactly is happening? What is going on in this population? So we can use, you know, the optical and UV light curves to model the accretion rate over time under certain assumptions and compare it to the radio onset time. So this is some work being done by Kate Alexander et al., which she's still working on. And this plot is from this upcoming publication. And what you can see is, you know, we have the radio data from that first paper shooting for the moon. We have, this is the rough date where if you had a delayed outflow causing this, that was a spherical outflow, maybe when that would be happening. And you can see the X-ray data here as well, the optical light curve. The point is, though, there's not actually very much happening at other wavelengths that would give away something dramatic is happening in the radio. Chandra observations we've been taking, it's pretty steady. There was some low-level X-ray emission when the TDE was first discovered. So there was some sort of low-level accretion occurring at the time. We're only within about a factor of 2, though, right now from that initial X-ray limits that we see. I should also emphasize, so AT 2018 HYZ is an in-house TDE. It was first discovered by Sebastian Gomez, who's here if you have any questions about its initial discovery. And I can't emphasize enough what a garden variety TDE this was at the time. There was nothing to show that this would suddenly become very crazy, something very exciting would happen. Yeah, so could this be due to something like an accretion flow state change? Is there something maybe happening in TDEs that's similar? It's very hard to say that just because state changes, you know, usually have some sort of X-ray rise happening as well. Some of these TDEs, though, I will say I didn't have time to show that. There might be some better X-ray radio connection. Not all the population, though, I should emphasize that. So what are some next steps? Well, the first step we could do is VLBI, which is, you link the radio telescopes from Hawaii across the United States, include Effelsberg in Germany for really long baseline. I put this here because someday in space, what is the future? It would be cool if we could do VLBI and put a little dish on the moon for that. Anyway, or in space, it doesn't matter particularly for me. But the idea was that, you have two models for what could be causing AT 2018 HYZ. Something like a delayed outflow, so hundreds of days after the initial event, you have some sort of non-relativistic outflow that occurs. That does appear to explain the majority of the population if you look at the physical parameters that we have in those systems. Or you could have potentially an off-axis jet where that emission has now entered our line of sight and we're seeing it brighten because as that field of view increases for our position on Earth. In the case of the latter, you would actually be able to resolve this TDE if it had superluminal motion that we could detect here on Earth. So we connected the radio telescopes across the country and into Europe to see what we could see. One observation in 1 year, and then we waited 1 year for the second observation. And I'm going to show you guys those initial results. So here is the first result from February 2023 with VLBI. And then if we add in the second observation, there's two things, it moved, it physically got bigger. The exact amount is still classified. We don't understand a lot about the noise and systematics that we have in this image, but you can see that the centroid size has also shifted. So we are detecting in AT 2018 HYZ a change. We don't actually understand a lot of it because if this is a jet, we think we actually have, it would be highly off axis and we would have a counter jet as well that is affecting our observation when the modeling of that is difficult. The good news is we actually have our third observation. Effelsberg was down for several months. It's back online. End of the month, we're finally going to get our third observation, which will hopefully then answer our questions. And we will be able to say, hey, look, we have a picture of what's going on. And isn't that really neat that we can do this now for TDEs? It's very exciting. But, so if it's an off-axis jet, we can also then take some models that some theorists have put out. So this is by Sunnygill and Pasbiani-Amini. If you considered a off-axis top hat jet with steep gradients as your potential source of the emission, by off-axis, like something highly off-axis, like 80, 90 degrees, not something closer. And then you could say that if it's an off-axis jet and you look at the various light curves, you're going to have a rise to about minimum 3,000 days at 20 gigahertz post-TDE. It goes all the way to 8,000 days, though, for that light curve that I was showing you in C-band. So, this is pretty cool because, I can go up for tenure and be like, you guys have to give me tenure and you'll never know what happens to HYZ and we'll see if it. So that's, the current prediction is this is still an object that we're going to actively be studying for a very long time to understand what exactly is happening in the radio. But yeah, so the other thing, though, is, as I said, it would have to be a very highly off-axis jet for this model to work, 80, 90 degrees off-axis. We can also actually tell this thanks to a model from Tetsuya Matsumoto, where basically if you consider the different angles that you have, this is gamma, like you basically would have unphysical values in your velocity if it was something very close to on axis to us. And we can also actually, I didn't show all the other plots here, but we can make arguments that basically infer from the VLA data that this has to be a very highly off-axis relativistic jet to be consistent with that. So it's a very exciting time for this. The VLA data will hopefully be on the archive in the next month or so, so keep an eye out for that. But yeah, I just wanted to wrap up with some open questions. So first of all, what is the future evolution of AT 2018 HYZ? We don't know when the peak happens until we observe it, but 3,000 days, 2 to 3 years, which would be about 2 to 3 years from now, or it could be even longer. We've been discussing here support for very long-term transients. I think we have a very good candidate for a very interesting, exciting long-term transient. So this is the sort of time scale we're talking about, years. Sometimes the exciting stuff starts happening, not just even months after the initial TDE. What multi-wavelength observations are there? Better sampling for a lot of this stuff over longer time scales. So X-ray data, we don't know when the radio starts to kick in. So, if we have X-ray when the radio starts, or at least a bit closer commensally, that could be very useful. all sorts of things over longer timescales would be helpful even after the initial TDE event ended. I would argue some of the exciting stuff really begins then. What are the implications for the rate of off-axis jets? So, as I said, AT 2018 HYZ was very normal when it happened. This implies, though, that because it was normal, that if we could find a lot more of these TDE events, and if this is an off-axis TDE that we're jetted TDE, then you could have a new measure of the relativistic TDE rate from the radio, because if there's more jets out there, okay, we have some that were pretty close on to us, like Swift J1644. You have very off-axis. There should be a population between. We could hopefully find them. And yeah, what are the other delayed TDEs doing? Because it's clear that the majority of these outflows are actually non-relativistic. HYZ was an unusual one. The picture is unclear. I think there could be multiple explanations for what's going on, but I will open the floor to questions. So thank you very much.
So just picking up on exactly what you just finished off on, what are the other leading explanations being considered for the rest of the delayed flare?
Yeah, sure. So there's some that, you have two peaks, for example. So a second outflow, Adele Goodwin done some very nice work on that. There could be a cocoon and then a jet eventually breaks out at later times. Odelia Trumbull did some work with Brian Metzger on this. There's some things about gas clouds, this and that. Maybe there's something about a density profile, like if you got to the Bondi radius, maybe you have some density change. I don't think that would necessarily explain it, though, because we're not seeing unusual densities in these environments. So still a lot of work to be done.
Have you looked at like a full VLA spectrum, like all the way up to maybe Q band? I couldn't quite see how dim it would be at that.
Yeah, so we usually go up to 25-ish gigahertz because getting up to Q band gets more difficult in terms of getting time and everything like that. And it looks like the peaks of these is roughly in the gigahertz. We have gotten millimeter data though. So yeah, so that was SMA data actually, Maurice. Yeah.
If your time scale for dropping will be fastest, I guess. Q band, SMA, maybe.
It only works for the very brightest, and we haven't had luck with ALMA, so yeah, that's difficult then for the faintest.
Brian, did you want to?
Yeah, I'm just going to ask, I mean, so even in a situation where you don't have a jet, but you just have something collimated that's non-relativistic, like a disk wind or something, and you should see the counter jet in that case as well, like, because it's not relativistic, right? So for your VLBI, I mean, is it clear that it has to be
basically
ultra-relativistic, or could it just be two non-relativistic column, like a cone-shaped?
Basically, the size of the centroid shift, you could then get a rough velocity from that, just because it's been a year between observations, and it would have to be very, very fast, relativistic. Yeah.
Okay, last question.
With the disclaimer that I'm not a radio astronomer, I'm wondering if there's a more efficient way to search for radio emission. Do you need the VLA because of sensitivity, or can you use a single dish telescope to just monitor the rise in the flux?
Sensitivity and resolution. You do get, good enough. Yeah, that's why we don't do single dish. Sensitivity, it turns out most of these, if you just look in the VLA STScI survey, you'll detect maybe 10% of these late time outflows. You'll miss 30 without dedicated observations. So.
All right, let's thank Yvette again.
Okay, thanks to the TDE group, we're back on track. So let's see, 2 announcements. First, splinter sessions are coming up at 3:45. If you liked how they went yesterday, keep up the good work. If you didn't like the way they went yesterday, bring that feedback to your splinter session this afternoon. We have, just to remind everyone, I sent out yesterday in Slack the room assignments. Go to that same link. I can repost it. Maybe I'll do that right after I talk. Go to day 2 tab. We have the high Z transients, which is going to be in here. Chair is Dave Coulter, and your scribe is going to be Armin Rest. So if you don't know Armin, that's Armin here. And this room is unlimited. So if you didn't subscribe to anything, I think you can still come in here. I think all the other rooms are currently at capacity. There might be a little bit more room in the high energy. So high energy observations, that's going to be chaired by Leo Singer in Cafe Con. There's Leo, and your scribe is going to be Suvi Gazari. And stellar populations and progenitors is going to be chaired by Nancy Elias Rosa and scribed by myself over in Bloomberg. So like yesterday, we're going to meet to go over to Bloomberg at about, let's see, it's 3:20, let's say 3:40. It takes about 5 minutes to walk over there. So we will meet in the lobby at 3:40. There's about 40 of us going over, so please be there on time. That should be about it. The other big announcement is tonight, as a reminder, we're going to have happy hour in the cafe starting at 5:30. We will then go, whoever wants to go at 7:30. I think it starts right at 7:30, so we might leave around 7:15, Uber over. Guilford Hall is this astronomy on tap, and we have a great lineup. So that's what's going on the rest of today. Anything else? Any questions? All right, coffee break. All right, cool. talking about. And then an hour